Bismillahirrahmanirrahim. Let us discuss some examples related to the Routh-Hurwitz criteria and how that can be used to determine the gain of a transfer function. Okay, so a closed loop transfer function is this one, C of s by R of s, that is given by this equation. And if I write down the characteristic equation, that is this one, so that you can see over here, setting it equal to 0 and simplifying this one, I will get this one. So if I develop the Routh table starting from this one, s power 4 1, and the next one will be 3, and the next one is k over here, and then s3 term 3 2 and the 0 over here. And if I develop this table, the entries will be like this, including the k. Now for the Routh stability criteria, we know that there should be no sign change in the first column. All of these entries should be positive. So here you can see it's positive, there is no sign change, no sign change. So what should be the value of k? What should be the range of k for which this entry will be positive? Right, so this part should be greater than 0. So we are going to write it like that 2 minus 9 by 7, k should be greater than 0. So if we solve it, so I will get that k should be less than 14 by 9. Right, so if our k is less than 14 by 9, that means this term will be positive and our system will be stable, because this is positive. So 14 by 9 over here, this will also be positive, so there will be no sign change. So if the value of k is between 0 and 14 by 9, because for 0 the special case of this Routh stability criteria will be applied. So the k should be between 0 and 14 by 9 to get the positive value over here to keep your system stable. So for the stable system, this is the range of the k. And for marginally stable system, that can be 0, because once this is equal to 0, that means our some roots, some poles lie over the imaginary axis. So if k is equal to 14 by 9, this will be exactly 0. So that is the value of the k for marginally stable system. Right, so we can change this k in this one. I have drawn this function over here, the transfer function, the system represented by this transfer function C of s and R of s, the closed loop transfer function in this one. And in this we can write this k over here, taking this transfer function outside. So if we vary this k, the roots of the closed loop system will change. Right, roots of the closed loop system, because for the closed loop transfer function we have this k in this equation, and when this k will be changing, the roots of this equation will be changing, so they will change their position. And if the k remains between 0 and 14 by 9, then the roots of this closed loop system will be in the left half plane and it will be a stable system. But if the k is not selected in this range, it is above, k is greater than 14 by 9, or it is less than 0 or equal to 0, then your system is unstable. For k equal to 14 by 9, this entry will become 0, and that indicates that your one pole pair is over the imaginary axis, so your system is marginally stable. Now we look at this example. A unity feedback system is given to us, whose feed forward transfer function is this one, k divided by s into s plus 1, s plus 2 and s plus 4. So if I write down the characteristic equation for a system which is like that, g of s and h of s is the feedback path, and there is a summer over here. So for this system, our closed loop transfer function characteristic equation is this one, 1 plus g of s into h of s equal to 0. Okay, so g of s is given to us and it's a unity feedback system. That means h of s will be equal to 1. So by taking those values, I can write down this characteristic equation, and if I simplify this one, so I can write this one, because this whole will be multiplied with that one, so plus k, and on this side it is 0. So this is our characteristic equation. So if I simplify it, I can write it like that, and now it is in the range form. I can develop the Routh table. So Routh table is this one, that now you should be able to develop, as we have already discussed in the previous videos. So if you develop this one, you are going to get this Routh table. So according to the Routh stability criteria, there should be no sign change over here. So this must be positive, this term, right? So taking this term for the stable system, this must be greater than 0. So we can solve it. What should be the value of k? K should be less than 14.70. So if the k is between 0 and 14.70, so that means our system will be stable. So if you are going to add proportional controller in this one, providing certain gain k, so that should provide the gain between 0 and 14.7, so that your system is stable. And for marginal stability, this will be placed equal to 0. So when it is placed equal to 0, the k comes out to be this one, 14.70, the worst case. If the k exactly becomes 14.70, this term will become 0. So special case of the Routh stability criteria will be applied, and that will be indicating that the pole is at the imaginary axis. Okay, now if this becomes 0, the whole of this term will become 0, right? And we will defining the auxiliary polynomial with the help of this term, 12.86 s square plus k, right? And setting it equal to 0, we can find out the poles which are on the j omega axis. So the solution of this one can be obtained like that s is equal to plus minus 1.07 j. So these poles are over here. Those are obtained from the auxiliary polynomial by when you have the zero array. Whenever you have the zero array, it means the auxiliary equation, if set equal to 0, will give you the poles over the j omega axis. Okay, so that is this one, 1.07 and minus 1.07. So two poles are at the j omega axis. So your system is marginally stable if your k is equal to 14.70. If your k is between 0 and less than 14.70, your system is completely stable, because then all the poles will be in the left half plane, because there will be no sign change in this column. Okay, now let's look at this example. Let's suppose that we have this polynomial and we want to determine the stability for that one. So first of all, we will have to develop the Routh table, s power 6, 5, 4 and so on. So taking the values from here, 1, 7, 14 and 8 for the first row, and for this one 2, 10, 8 and the next entry is 0. Okay, so these are the first two rows. So if we develop the Routh table, here you will see that in this row s power 3, all the entries are 0. So it's a rows of 0. So we will have to define the auxiliary polynomial. So we have defined this auxiliary polynomial using the row just above this one, s power 4 row. So 2s power 4 plus 10s square plus 8. And if we take the derivative of this one, we are going to get this one. So we are going to replace this row now with the derivative term. So you can see 8 and 20, those are coming from here, from this equation. Right, and then moving onward, the row for s square, and then row for s power 1, and then row for s power 0. Okay, so here you can see that there is no sign change. There is no sign change. So what that means? It means that your system is stable, right? But as you have the 0 row in this one, so if you have written the auxiliary polynomial, so for marginal stability you can determine where will be the roots over the j omega axis, because whenever you have the 0 row, and if you set up this auxiliary polynomial equal to 0, you can find out the poles over the j omega. So taking this equation, setting it equal to 0, solving it, so you will get these 4 poles. One pole pair is plus minus 1j, and the other pole pair is at plus minus 2j. So that is shown over here. The poles are like that. So poles are not repeated. In one of our previous video, we have seen that if the poles are repeated over the j omega axis, then your system is unstable. So this system is not unstable. This is marginally stable, right? Because of the poles over the j omega axis. But overall this system is stable because there is no sign change in the first column. So your system is stable. Okay, now let's look at this example. Let's suppose our transfer function is this one, and we want to look at the stability of this one. So for unity feedback for unity feedback system, the characteristic equation will be 1 plus g of s into h of s, that should be equal to 0. So g of s is known to us, that is g of s. So unity feedback h of s will be equal to 1. So we can write down the characteristic equation like that, and if I simplify this one, I can write it like that, because e raised power minus st is approximately equal to 1 minus st, right? So replacing this e raised power minus st using this um, approximation, so we can write the equation. This equation first of all written was like that, and from here by using approximation we can write it like that, and if we rearrange we will get this equation. Now we develop the Routh table. So s square row and then s power 1 row and then s power 0 row. So for the system to be stable, this must be positive, so 2 minus t should be greater than 0, so t should be less than 2. So if t is less than 2, your system will be stable, right? So there is the condition over this t, or the tau, the time constant of this your circuit, that if your tau is less than 2, then your system is stable. So if it is greater than 2, there will be a sign change over here and your system will become unstable, right? So the stability depends upon this thing, right? Okay, now let's look at this example. Now, open loop transfer function is given to us, that is this one. So characteristic equation will be 1 plus g of s into h of s equal to 0. So setting the characteristic equation, simplifying it, we will get this polynomial. Okay, so now we can develop the Routh table. The Routh table will start from s power 4, because the maximum power is this one, so 4, 3, 2, 1 and 0, and taking the coefficients from this equation, and this is the Routh table. So in order to have the stable system, this must be positive, so this is set equal to greater than 0, and if we solve it for k will be equal to 11.56. So the range of k is from 0 to 11.56 for the stable system. If the k is outside this one, then it means your system is unstable. Okay, now looking at this example, this is the polynomial given to us, and we are supposed to find out the stability. We need to comment on the stability. So if we develop the Routh table, so you will get the zero entry at this row. So as we have already discussed, we can do it by replacing this 0 with the epsilon, or you can replace the s with 1 by z in this equation, and you can develop the new Routh table to determine the stability. So first of all, replacing the 0 with the epsilon, and then moving on as it is with using the Routh stability table development rule, and then we apply the limit, that if this epsilon is approaching to 0, what will be the value of this one. So applying limit over it, limit epsilon is approaching to 0, 3 into epsilon naught plus epsilon plus 4 by epsilon. So if we set up that one, so we get positive infinity. Okay, and then if we apply the limit over this one, right, so this will give you minus 4. So this table now can be written like that, if we assume it in epsilon, this will be infinity, then from infinity minus 4, and then 8. So you can observe sign change. This is positive, this is positive, but this is negative. One sign change over here, and then from negative to positive, one sign change over here. So two sign changes, so two poles in the right half plane, and it's an unstable system because there is the sign change in the first column of the Routh table. And if we use the second method, in the second method we will be replacing s with 1 by z, so you will get this polynomial. And if you develop the Routh table, so again you will observe that positive to negative and then to positive, two sign changes will be there. So it means there are two poles in the right half plane, the system is unstable. So either you can use the first method, or you can use the second method to look at the stability of your system. So let's conclude our discussion of the Routh-Hurwitz criteria. We have seen number of examples. We have seen that how we can determine the range of the k, that's the gain of your transfer function, so that your system remains stable. Because if you change the gain k in the open loop, that will affect the position of the closed loop poles, right? So if I quickly draw it over here, the k was over here, and this is g of s, right? And then h of s, the output is over here, c of s, and uh, input is r of s. So if you change this gain k, So that will change the position of the closed loop poles, C of S over R of S, that is whatever it is. So the poles of that closed loop transfer function will get changed, and that will change the stability. That may change the stability. For one particular value of the k, your poles may be in the right half plane. You may go into the right half plane, your system will become unstable. So we have seen in this video that how we can determine the range of k for which our system will be stable, that there is no sign change in the first column of the Routh table and all the poles are in the left half plane. So that's the conclusion of this lecture, that you must be able to now determine the value of the k, the gain that is introduced in the open loop of your open loop transfer function of your system, and how that gain k controls the position of the closed loop system, right? So that's the conclusion, that you should be able to determine that value of the k. That's all from this video. Thank you very much.